Friends, in this video I'm going to show you how we can perform die structure analysis, also known as die validation. So why this is important? In press tool designing, for designing of various components of the press tool, we use various formulae, thumb rules for determining the geometric parameters of the components. But these formulae and formulae are nothing but empirical rules or thumb rules actually, which may not stand accurate every time. Sometimes you may design a overly designed model of the components, or it may be critically designed. It may fail under operational loads. So there must be a specific way to designing of these components. Of course, what we are going to do is we are going to import the model which is designed with the help of these empirical rules or formulae, and we're going to analyze that model using the map loads of the operation, and we're going to verify whether it is failing or not failing. If it is not failing, then what is the margin of safety? If it is too high, then we can reduce it so that we can have lower material. We can lower the weight, costing of the tool. We can appropriately have the reasonable. We can appropriately design the model in such a way that it will have a reasonable factor of safety. Before going to that, let me show you what the final results that we'll get using this. So it's one of the component of the tool. So you can see here, you can directly see the maximum stress incurred in the component, and then for each component I can view the results, and I can appropriately determine what is the distribution of this stress, and likewise also this is the summary of the analysis. Here you can see the factor of safety is 1.8, 4.9, which means actually these are safe, but you see die riser is critical, die shoe is of course failing, and now here you can see the housing is having very high margin of safety, which is not required by the industry standards, means our industry standards. I can reduce this factor of safety. I can have that reasonable up to less than 2 or around 2. So this can be done. Means I get idea that tie housing is over designed. I need to rework on that so that I can have that reasonable margin of safety. Of course, and die shoe, I need to increase the material so that I will have again reasonable factor of safety. So this conclusion can be obtained using by viewing the results. So that's why we perform die structure analysis. So it's kind of die validation, because means you can validate your design concept with this analysis. So let's just start with it. For this purpose we are using the Altair HyperWorks, HyperForm and HyperMesh, and its basic FEA. These are actually user profiles of the HyperWorks software. Right now we are in the HyperWorks HyperForms die module user interface. So now we are in it, and we are going to import the components. So in the die, so while importing, I suggest you that you should export these components from the CAD software in the IGS or step format, whatever it is, but export them as a separate component. Don't export them as a single tool component, so that we will have separate components, and we can establish proper contact definition in between these components. For that purpose you need to export them separately. So I am importing these exported geometries separately, like this. Okay, I'm actually working up to lower half assembly only. It will be extended to upper half assembly also, but right now for this demonstration purpose I am working only on the lower half assembly components. So this is my lower half assembly component tool. This is lower half assembly tool. I may excluded the other components like guide pillar post, stroke end blocks, low lifting studs, because they are not concerned with the operational loads. uh, and of course you could import lifting studs for carrying out the transportation analysis. In demonstration purpose I'm showing you only operational load analysis, or the analysis with only operational loads. That's why I have skipped lifting studs. So what we gonna do actually, first of all let me tell you that in the HyperWorks Hyperform die module you got this operation option, die stress analysis and die optimization, which are actually specially designed for this kind of application. But actually this is designed for casting type of tools. This is preferable for casting type of tools, where you have most of the components integral with the casting. Here in the plated type of dies you have separate components which are fastened using the fasteners like bolts and dowels. Here you have to establish contact definitions between these components separately. This cannot be done with these options like here die stress analysis or die optimization. As I said, they are preferable only for casting type of dies. So here in this method I'm going to be showing the demonstration for plated type of dies only. Of course we will be using die stress analysis where I will show you later on. So right now we need to get into HyperMesh. Means I prefer to mesh models in HyperMesh user profile. So I'm getting into HyperMesh radios. Okay, so right now we are in the HyperMesh radios GUI where I find meshing and geometry editing quite easy. You have a lot of options right in my HyperMesh user profile. We'll be meshing these components separately, of course, as they are separate components. First of all, let's rename them. It's bottoming plate. This is die block. This is die housing. Oh god, I'm repeating these words. Fine. This is die riser. This is lower shoe. Fine. Now we'll start meshing it. First of all, let me clear with this thing that uh, you must check this whether all these components are need any geometry modification or not. Of course I could delete these holes and make it plain, but that's of course for demonstration purpose I'm skipping that. That's a lengthy process. So before getting into this, you can suppress the unwanted geometry. You can edit the geometry as as you feel comfortable with it, and then after geometry editing you can proceed for meshing. So I'm using here 3D meshing, tetra meshing. In that volume tetra I'm using the solids. I will be meshing using the solids. Right now I'm meshing bottoming plate, so I have activated that component. And the 2D types I prefer to use are triads. Of course they are stiff, but still, as I said, for demonstration purpose I will be keeping the things simple. I'll be keeping the element size also bigger one. This is also not recommended because the element size greatly affects the performance, accuracy of the output. Of course it also increase the solving time, but as I said, for demonstration purpose I'll be quick and fast. That's why I'll be keeping this bigger. Now after bottoming plate I'll activate die block. Yeah, I prefer to keep the consistency, and that's why I kept the other parameters same. So likewise I'll be meshing all these other components by appropriately activating them. So now I have meshed all the components, and they are in their separate components. The mesh is in the separate components, and now the next step is to check the quality of the mesh. This is very important that you should check the quality of the mesh, and then if it is not acceptable as per the industry standards, you can refine that. You must refine that. You must check the type elements types such as the Jacobian warpage. Likewise, you correct everything. There should not be any failing in any element filling the criteria of the mesh as per the industry standards. And after that means you will have then better accuracy in the results. After performing this check and then refining of the mesh, I'm skipping that actually because that's of course not a easy task. That's time consuming and lengthy process. Therefore I'll be skipping that. Then for the demonstration purpose, now the next step is to establish the contacts in between these components. This is important because when if I just map the loads and give the boundary conditions and perform the analysis, what I will do, the loads will be only mapped onto the die component. So die component is on, and the constraining will be only done and the for the lower shoe. The rest of the components have just imported into the software doesn't know that actually die block is resting on the die riser, and its tree size are supported by the die housing. These things are not known by the software. These are to be conveyed to it, and establishing contacts in between these components is kind of way to let the software know that there is what kind of relationship is in between these components. That's why we will be establishing that contacts. So the contacts can be established in this GUI radius, maybe HyperMesh in HyperMesh, but I found another way that I get into basic FEA user profile, and and from this user profile maybe it's quite easy to establish those contacts. And now I'm right in the basic FEA user profile of the HyperWorks. Okay, what it has done actually, it has deleted some of the component mesh. This is actually wrong, means actually somewhere there was mistake. So I think that was see, die block has two blocks, means there are two objects of die block. Similarly for die housing there are two objects. So it has separately created those components automatically, and it could not automatically mesh them. So what we should have done, we should have separately imported these objects as with these different names, of course. So that would be done in the first stage, but it's fine. What we have to do again is to again mesh them. So that is actually lengthy again. I'm sorry for that. I'll be pausing this video and then I'll get back with the mesh model. Okay, now I have again meshed the model, complete model. Let's just, now we don't need surfaces, so we'll hide them. Okay, let's just see which are these components. Okay, my mistake, it is actually, it should be die block 1 and that should be die block 2. So we'll make it right here. Oh, I got the error because actually there will be two components with the same name. I must have renamed it something different. Let me just get back to you again. Okay, this should be renamed as, I just, now this will be two. Okay, now this one as dialog 1. Okay, now let's check whether it is fine. Okay, now we have the mesh model. It would be passed by the quality checks also. About the contacts, get into the basic FEA model browser. In the contacts, we can create the contacts one by one. I think it's hanging again and again. I must save the model first. Okay, now I think I must restart this. I think basic FE is I don't know why it's so heavy. I never seen such slow response in the HyperMesh or any other user profiles. Basic FE is kind of weird, but still, just for making just I thought contact making contacts in this in this user profile is quite easy. I just use this option. If you find anything else in the, I think in ANSYS user profile, you can make the contacts. Okay, I was probably found the reason why it was hanging. I just on the surface mode, means I just unhide the surfaces, and now I think now it works. Still it hangs, but still it works now. So wait for some time, it will show you the options. Okay, now the contacts in the create option, you can select the auto contact option. So now it is expected that it will automatically create the appropriate contacts in between these the appropriate components, particular components. You can see the progress. Okay, maybe it's completed now. Okay, these are the contacts, so we must check them. Bottoming plate and die riser, that's a wrong contact, we must delete it now. Then bottoming plate and die riser 2, that's also incorrect. In bottoming plate and lower shoe, yes, there is a contact. lower shoe and die riser 2, yes, there is contact. Lower shoe die riser 1, yes. Die block die riser, yes. Die block 2 die housing, yes. Die block 1 die riser. Die block 1 die housing. Die housing 1 die riser 1, and then die housing 1 die riser 1, yes. Die housing 1 die riser 1, die housing 2 die riser 2. Okay, now this contact was incorrect. 1. Okay. Okay, that's all. This was the purpose for the basic FEA user profile. Now will we get back into HyperForms die module, where this will be utilized for just for the mapping of the forces. In that, go to tools and die stress analysis. It will invoke the process manager. That's a kind of mm, model browser. Save the instance. Actually we don't need that later on, but still just for getting forward, create it, save it. Now this is the process manager GUI. I'm closing the user process. Okay, there we go. In the process manager model browser model, we can see tool material still, that is say apply. You have, I think, aluminum and titanium as other options. In the second step, it's asking for the result file. You can select appropriate solver in which you had solved that, by using which you had solved that forming simulation earlier. Means it is important that before getting into this raster analysis, you must have the solved model, or you must have done the incremental forming simulation for the part for which the tool is designed. So just browse to that file, incremental, and then just browse to any one of the A00 file and say apply. Now it will I think invoke the hyperview window, from which it will get the results. Now it's asking for the result part, and I want that to be die. I'll say apply. Now it will extract the forces from the die component, and now it's asking for me asking me to select the structural part to map the loads. Means from these the extracted loads will be mapped onto this component. So I'll want it to be die block 1 as well as die block 2. So I'll just select and proceed and apply. Now it will map all those loads onto the die component, die block. Okay, that's all. This was needed. Means die module dash stress analysis or the process manager was only to be used for the mapping of the force. Now we don't need anymore this die module. We will get back into HyperMesh profile, user profile. Here we can establish. Here now we have got. I will select OptiStruct as the application. It's this you can select radius also. That's just a different solver. Now I don't need process manager model browser, so I will delete. I will in a view from the view options, I will uncheck that model browser visualization. I'll say no. This was the I just temporarily created that for mapping of the loads, so I didn't save that instance. Now I'm again in the HyperMesh. Here you can see automatically a load collector of operational means actually operational load has been created, that because of what we did in the die module high stress analysis process manager. Now uh, as you can see, if we just zoom in into this component, you can see all these loads are created. These loads, by analytical calculations, it is very difficult to map these loads onto the appropriate component, because you cannot say it directly, you cannot directly say about magnitude, conclude about magnitude of the forces, as well as even if you say something about magnitude, the distribution of its I'm sorry, even if you can conclude about direction, that you cannot comment exactly accurately about the magnitude distribution. So because you see, there are a number of elements, and on each element it has mapped different loads. So this is by analytical calculations or by manual processes, it's very difficult. So now you see, one of the load characters created, to create the load step of linear static analysis, like here you need some constraining. So that's constraining is what will be the next step. uh, Before I proceed to the constraining option, constraining step, we have established the contacts in between these two components. Let me hide the loads right now. Okay, we have established the relationship in between, the contact relationship between it in between these components, like die block, die housing, die riser, lower shoe. They are just, sir, they have just surface contact, but there is additional contact of bolting or doubling. That's because of the fasteners. We have constrained their degrees of freedom, so that also must be considered. Now here I have made uh, practically wrong but logically correct, or logically correct assumption that I'm I'm actually using the bolts uh, with rigid property. Means I'm assuming that the bolts are not deformable, they are rigid. This is this is not a practical case, because most of the time bolt has fasteners have failure, and but because fasteners, as you know, as standards cheap and we can easily replace them, we do not need to bother about them. What our concern must be about the failure criteria of the other components or the important components, stack components. So if you make the bolts rigid, these loads will be directly transferred to the component, and we get the appropriate stress distribution, which may not be exactly practical, but as we are concerned with their failure or the failure criteria, we need to make the bolts rigid. Otherwise, all the failure will occur only at the bolts, and there will be no stress distribution across these components. So that's why I'm making bolts as rigid components. If you want them to be deformable, you can do that using creating the separate component and then applying it separate properties, and then mesh them using 1D elements, but with the as I said, deformable property, material property. So I'm now creating the rigid components for fasteners. In the rigids I have it's a activated component. Now I will go to 1D. Oh, before I go to 1D, I must create node points. So for node points, I pressed F4 key. Now my bolt starts something from this counter depth. I'm selecting the peripheral or circumferential points. Now I will be saying circle center. Then the lower portion of the bolt where there will be threading, I'm selecting any 3 points along the circumference of the circle, and I'm creating the center point of that circle. Now in the two nodes panel, I'll be selecting these recently created nodes, and I'll say nodes in between. So that's newly created uh, point is nothing but a kind of centroid of the bolt. So from this point I'll be creating number of rigid one dimensional rigid joints, rigid elements, correcting all the periphery of the bolt hole. So as a independent node, I'll be selecting this centroid like element node, and then for dependents I will choose multiple nodes, and in multiple nodes I'll be selecting these peripheral points. Then I'll choosing this biface option, by which I'll be able to select all the circumferential elements, sorry, nodes. Okay, I think I need to clear the nodes again, and I have to work again with that. It's better to select more than one at a time, and then by choose this option biface. Okay, now it is properly selected. Maybe it has skipped this. We need to make select them manually. Okay, now as you know, bolt is used to constrain only the vertical degree of freedom, means in this case the z direction. So that's why I'm constraining only z direction. Okay, the bolt this is created. Now similarly for bolting, we need to again create the center points, center nodes. For clearing the unwanted nodes, I pressed Shift F2, and I'm just selecting the unwanted nodes and I'm clearing them. Now this is what my required independent node is. I'll be selecting that one and selecting the circumferential nodes and say biface. Okay, I think this was not selected. Okay, you perform these things perform these creation of the rigid components on all the bolts and dowels appropriately. I'm just doing it for two of them for demonstration purpose, and of course, and uh, as you know now that dowel is used for constraining only lateral moments, lateral degrees of freedom. That's why I'm constraining only x and y directions. And say create. It has created. As I said, likewise you prepare bolts and dowels appropriately for all these components where you have provided the holes. After that, after creating all these things, you need to create another load collector. Oh, most important thing is your component, I'm sorry, your press tool is going to be attached to the, not attached but fixed to the bolster plate from these along at these at these locations of the clamping slots, that is at these 4 locations. So at these 4 locations you need to create the node points where you will having where you will be able to constrain provide the constraint load collector. So first of all, create the node points. In a similar way, I'm adding these temporary nodes, circle center, and then 2 nodes. Okay, this is the center point of this clamping slot. Now at, I'll be creating a load collector named as SPC, single point constraint at the clamping location. So this will be used for constraining. This will be just like uh, fastening the of the lower half assembly onto the bolster plate. So for that I'll go in analysis and in constraints, and then in constraints I'll be selecting this node. Actually, before I do that, I must create the rigid elements right here using this node as independent, and then this node as my face. Okay, this is created. So this is the important point. Now we can constrain this point using analysis and then constraint, and then select this node and uncheck the rotational degrees of freedom, but all lateral or all linear degrees of freedom. After that say create. So it has created this constraint SPC clamping. Likewise you prepare constraints for all these 4 clamping locations. I'm just for demonstration I'm just showing you for the one clamping slot. After this all is done, you have 2 load collectors which are important for creating the important for creating the load step, completing the load step. So in the load step now you can create the load step, and it's named as operational loading. And then in check on SPC and loads. In SPC select SPC loads, operational loads. After that in the type as linear static analysis, and just say create. After that it has been created, new load step. You see material and property has already been set and updated as we did in the as we did the steps in the basic FEA and in the die module. So you don't need to worry about that. After that after load step is created, now you're ready to solve the solution, solve the model. I'll be using, I think, Radios solver for that. So I will get into Radios user profile. So in the analysis, again go to Radios, and then here you can export all option, run option as analysis, and then you can hit the Radios button. It will solve the HM file, the model in the HM file. After that you can view the results using HyperView. So this is all about this linear static analysis of the die structure, that we can also call it as die stress analysis, also maybe die validation. So the most probable errors that you can that can occur are the meshing quality, the Jacobians, and maybe the skew errors. They are to be carefully solved. After that, the contact establishment is very important. That can be something somewhere that's a difficult task, but still using the basic FEA, it's using automated contacts, you can easily do that. After that, the most important step is the mapping of the loads, that we have done using the die module. die stress analysis process manager. And the for the bolting, that's quite weird that we have not considered the practical aspects of the bolt, but still, for the design, for this just analyzing or validating the design, it's quite it's quite logical to make the bolts rigid. That's all. Thanks for watching.